Hey folks, quick mini lecture just talking about a review of cross products. I have drawn out kind of what we talked about in chapter 3 with our vectors A, B, and C. So we said that vector C is equal to the cross product of A and B, or A cross B. I want to actually translate that into exactly what we're talking about for torques, so that way there's really no confusion about what letter goes with what. A is going to be R, B is going to be F, and C is going to be tau. So I have R cross F equals tau, but I could talk about the general A cross B gives me C. And if you're taking Physics 2 in the fall, I'm going to keep kind of coming back to this. Cross products don't go away. We're going to have a lot of cross products in the fall. Not a whole lot, but it's going to be key. It's going to come back and maybe with a vengeance. So if I'm just gonna stick to the concrete example here. If I think about R as a three-dimensional vector, and we do need 3 dimensions. Cross products are inherently 3-dimensional. They are 3-dimensional. So we're going to say that R is equal to Rx, comma Ry, comma Rz. And then F is going to be similar. I'm going to have Fx, Fy, Fz. So now when I talk about tau, if I talk about tau as a vector, right, I need to think about this cross product. And we said that I'm basically taking the determinant. That was something that we said back in chapter 3. We're taking the determinant. So the x component of tau, it can be calculated as Ry Fz minus Rz Fy. That's going to be the I hat. I'm mixing notations, I know, but this is going to be the I hat component, the x component. We're going to subtract then our Rx Fz minus Rz Fx, and that's our j hat, and then plus our Rx Fy minus Ry Fx, and that's our k hat direction. So we have a 3-dimensional vector popping out of 2 3-dimensional vectors, right? Even if it's a 2-dimensional vector, we're still going to need to have that third dimension there. We're just going to label it 0. So the reason I say it's inherently 3 dimensions is, let's say I have some, some r here. My r vector and my f vector is just in the y direction. All right, so these are just x and y vectors. If I think about just x and y vectors, whoop, whoop, right? No z's, well, that means that all of this is 0, all of this is 0, and I'm just left with z for my torque, which means, right, my torque actually pops out in the 3rd dimension, right? So it is inherently 3-dimensional. There's nothing we can do about that. So start thinking about x hat, y hat, z hat, or I hat, j hat, k hat, or just our 3 dimensions in our pointy brackets, just so that way we're not unprepared. Now, how do we know which way tau actually points in that 3rd dimension? Whenever we do a cross product, if I have 2 vectors, let's call them A and B this time, and some angle between them, C will always be perpendicular to both A and B. All right, C will by definition always be perpendicular to both A and B. All right, so this, if I'm in x and y, I have to have a component in z at the end. We're going to talk about how to find that direction of the torque, or the direction of any cross product, really, using the right-hand rule, but we're going to talk about that in the next lecture video. I think I'm out of time for the 5.5. I'm really trying to keep these short. So I'll see you back here next time. Have a good one.